Start recording, share my screen. I did turn up the volume. Okay. All right. Get rid of this stuff. Okay, so we talked about why you want to do statistics in the basic samples. The population is the entire set of data items that you're dealing with, and the sample is the subset of that. And the reason you do the subset is because it's generally not feasible to do the entire population. Distribution is it's hard to define that without using the word distribution, right? It's basically the way in which the probabilities lay out, the way they relate to each other. Mean is the average. Variation is a measure of how fat the curve is. It's telling you for each individual how far they are off from the mean. And there's a squared term in there so that the negatives and positives don't cancel out. And then deviation is just the square root of that variation. And then we talked about briefly talked about different distributions. The even distribution or flat distribution, that's generally what you use for a single event. Like think about it. If you have a single die, one die, and you roll the die, if it's a fair die, you have a flat distribution, 1 through 6, or 1 through 20 if you're playing D&D. And then if you're flipping a coin, the idea is it's a fair coin, you have a flat distribution, 50-50 heads, tails. By the way, in reality, I forget, I think it's heads is like 0.50041, and tails is like 0.49949. I can't remember how they figured that out, but it's because of the shape of the engravings on the coin. Now, that's for a US quarter. Anyway, if you don't want an even distribution, you are allowed to weight it. So you say, okay, I'm going to do my random number generator, and it's going to give me an even number from 0 to 1. And if it's from 0 to 0.75, I'm going to do A. And if it's from 0.75 to 1, I'm going to do B. You've just put a weighting in there, right? It's no longer truly a flat or an even distribution. By the way, we talk about computers providing random numbers as if they were random numbers, but you've probably heard the term pseudo-random, which means what? Not really random, right? Pseudo-random. It's not really random. So one of the things you do have to pay attention to when you're doing computer modeling and simulation is the fact that your random number generator is not truly 100% random. Now, is it good enough? Virtually always. Virtually always. There are people out there who are trying to develop ways to generate actual true random numbers. In fact, I think that's them. Yeah, whatever. I don't care. So here's a group of people who are trying to develop true randomness, and there's tools on here. If you need to do some quick random number generator, you go to random.org and use some of their tools. So the idea here is they're using whatever techniques they're using. I think they're doing weird noise from the natural world. I think some measuring stuff in the magnetosphere around the Earth and things like that. But that's their goal. I have also seen where people who were developing a simulation didn't want to use the pre-canned random number generator that came with, in this case, it was Java. They built their own function. Now, why did they do that? These are things that you have to pay attention to when you're doing computer modeling and simulation. then there are things that you know not necessarily would pay attention to until you run into an issue. Any guesses as to why they didn't want to use the Java random number generator?
My guess would be that it has a sort of pattern to it.
Okay, it's a good guess. I don't believe the one they developed was any more random than the one that Java came with. In other words, they were both pseudo-random.
Then would it be that other people have access to that random that Java makes?
Oh, you're getting closer, yeah. Think about how Java works. This is where you have to know your tools, right? Know your languages. How does Java work? Java does not compile to an executable code. Java compiles to a class file, which is bytecode, which is then interpreted by a Java virtual machine. The Java virtual machine then will have an implementation of the random number generator. The Java virtual machine for Apple and the Java virtual machine for Windows and the Java virtual machine for Unix are not the same, and they may have different random number generators in them. And so what these people wanted was a unified, no matter where we deploy, we want the same random number generator. So we're going to build our own and call ours. And that way, when we put it on Unix or Windows or Apple, it doesn't matter. We get the same behavior. That's a pretty subtle line of reasoning that I think a lot of people wouldn't pick up on. And let me ask you another question. Yesterday, I was saying random number generation is great for simulations, and it is. We don't generally look, other than in physical, modeling physical behavior, we don't generally like it when our simulations always come up with the exact same results. So we do want some randomness involved so that we get a range of results, particularly in an agent-based system, where we get a range of results and then we can do our statistics on the range. Is there a time where you might not want randomness involved? Yeah.
Maybe like a surgery. They extent of like,
No, I'm talking about in a simulation.
yeah, like they have medical.
Oh, okay, okay.
So I'm thinking like you wouldn't want randomness of like the.
Oh, yeah. Okay, okay. Right. Let me phrase it differently. You're exactly right. Yeah, that's a good situation where you don't want randomness because you want the actual behavior. Same with like almost any training simulation. If you're training a pilot, you want the plane not to behave randomly, right? You want it to behave according to the physics of the aircraft. But let's say you have an agent-based system and you have randomness in there. Would there be times when you would want to effectively turn off the randomness and have a deterministic system in the exact same simulation? If you're doing your UAVs and there's some randomness as to the routes and the number of UAVs and blah, 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 would there be a time when you might want to turn that off?
When I would want to look at like a specific scenario.
Right. So we're going to talk next about verification validation, but think about debugging. When you're debugging something, if an issue comes up, what you want is to be able to repeat the exact same behavior to find out what caused the problem so that you can fix it. Or if you want to replay a scenario to see what's happening, like some scenario, something really interesting happened and you want to find out what it was, how could you possibly recreate that scenario? You can only do it if the same decisions were made leading up to the point of the interesting behavior. So in that case, you want to have a way of turning it off. I don't know how Java works, but many random number generators, if you call the function without an argument, you get a true random number. If you call the argument with a number or some kind of a value inserted in there, so you have an input parameter, then that's generally treated as a seed. And if you have a seed, then you will get a deterministic result back. So you can control the randomness by putting in a seed or not. And in some systems, if you put in a seed, not only will you get the same number back every time for that one function call, but every function call after that is based on the result of the previous one. So you get a sequence, a deterministic sequence that's repeatable. So there are times, again, it depends on the language. So there are times when you're either developing your simulation and you want to do a specific tests, or you found something wrong and you need to debug, or you found an interesting scenario and you want to explore it in more detail, where you might want to turn off the randomness in your system. So you just have to be aware of all of these things. Just know everything and you'll be okay. Come on. Okay. Okay. Yeah, then we talked about different distributions. The flat distribution, like I said, for single events tends to be. I'll get off this point in a minute. Here's a question. If you have, I said if you have one die and it's a fair die, you get even distribution, right? It's 1 through 6. What about 2 die? If you roll 2 die, now the outcomes are between 2 and 12, right? Snake eyes and boxcars. Is it an even distribution? No. What's the most common result? Well, let's see. How many ways are there to make snake eyes? One. How many ways for the number 3? 2. The number 4? 3. Number 5, 4, number 6, 5, number 7, 6 ways to make a 7. And the reason there's 6 ways to make a 7 is if you think about rolling the first die, you're going to get a 1 through 6. Every one of those, it's possible to get 7 from with the second die, right? So there's 6 ways that you can get the 7, and then 5 to get 8, and 4 to get 9, and right, and it goes back down. So it's actually a bell curve. What if you wanted a flat distribution? Could you do that? I remember distinctly when I was, I took my undergrad here, by the way, and there was a terrific set of mathematicians teaching at the time. In fact, Jacob Elliott. Did anyone have Jacob Elliott? Elliott Jacobs? No? Okay. He was here. He still may be teaching. Dr. Thomas Hilburn. And anyway, these guys were great. And I was playing around with games and I thought, man, I want to have a dice roll, but I want to have flat distribution. And so I asked Dr. Hilburn about it, and he couldn't come up with a way to do it, and I couldn't come up with a way to do it. And the answer is stupid simple. Can you think of a way to do it? How to get a flat distribution? You take one die and color it blue, and one die is white, and then you read blue, white. So the numbers that you can get are 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4. Basically, it's a base 6, right, counting system. And now it's a flat distribution, and you've got 36 unique outcomes. Be aware of how to be able to combine things, right? Odd situations come up, and you may have to invent ways to deal with them. I did not come up with that solution. That came up from a Avalon Hill game. All right, so even distribution. Then geometric distribution goes out to the first failure. Poisson distribution is commonly used to model time between 2 events. So if you're doing some kind of a queuing model, like you may use a Poisson distribution to say how, here's a particular launch pad. A UAV just took off. How long before the next one takes off? That might be something you could look into. And then, of course, the normal distribution, which is what all our statistical tests that we discuss normally are based on. Okay, so now let's talk about tests. And look at some quick examples, and I'm stealing them from online. I'm open about that. There are more online examples of statistical tests than we could read in our lifetime. So by all means, don't sit and stew and wonder about how to do these things. Look for the test and follow the model. All right. So first of all, degrees of freedom. That's the number of choices that we have -1. This is the n-1 thing. It's the degrees of freedom. And so why is it the number of choices you have -1? If you have one choice, do you actually have any freedom at all? No, right? So you have 0 degrees of freedom. If you have 2 choices, left or right, then we're going to say you have a degree of freedom of 1. It's always the number of choices -1. So in this case, it's the number of samples -1. So z-test, it's defined, let's make this better. Capital X bar minus mu over sigma over square root of n. What the heck is that talking about? What is being done here? What's being compared? Capital X bar is the observed average or mean, and mu is the population average or mean. So what are we really doing? We're comparing 2 means. And what did I say the other day? In statistics, we're always asking the questions, are these 2 things the same or different, right? Are these 2 barrels full of marbles the same or different? Are these 2 samples of students the same or different? And so what's happening here is if we say, look, we know from testing across the nation that globally, we already know what the population average is. Now, you've got some students that you did this teaching intervention, you wrote a new textbook and you want to show that your textbook actually improves the scores of the students taking the test. So we're going to look at your students and that's going to be our observed average. And we're going to compare it against the known population average. Notice you have to have a known population average. Oh, okay. So if that's the known population average, then we're going to compare those 2 averages. And if they're different by a little bit, we don't know if that means that your textbook's any good or not. If they're different by a lot, we're going to say, okay, we think your textbook is really helping these students. Where's the line? Where's the line? And that's what this thing is coming down to. You're basically comparing 2 populations. Now, some of these, I'm saying we have a known population for mu. Sometimes this is the before and after question. Oh, okay. I'm going to put in time delays in my, right? And for a fuzzy cognitive map with 10 nodes, on average, it takes 100 time steps in order to converge, on average. And then I put in my time delay, and on average, it took 110 time steps for it to converge. Is that a meaningful difference or not? Did that affect things or not? And so now you've got 2 averages, right? On average, it took 100. On average, it took 110. There's some width to that, right? There's some deviation from that. So then the question is that significant or not? Is that meaningful or not? And that's what this test is about. And you'll notice what it's taking into account, the top's pretty straightforward. It's just the difference between the 2 means. The bottom is taking into account with sigma, the fatness, right? The deviation. So as you would expect, if you had a population, and let's put the average right at 0, right? Just for easy. But it's a big, wide, fat population. It's going to have a large deviation, right? Then we would expect that when we do our X bar, we could have larger variances or larger offsets from that 0 and still claim it's not statistically significant because we said that it's a big fat curve. If it's a really tight, narrow curve, and then we can't allow X bar to get very far off of the average, the previous average, without saying it's statistically significant. So that's what the sigma term is doing in there. And then square root of n is square root of the sample size. And again, I would love to derive this formula for it. I don't have the skill set for it. Anybody? I'm sure it's online. I should look it up. We use the z-test when we have 30 or more 30 or more in our sample. And that's a weird number because it doesn't depend on the global population. It's just I have 30 or more in my sample. And then the t-test is very similar, but we use it when there's small sample sizes. It's generally considered to be less than 30. So what's happening? We are comparing two means and trying to determine, is there a real difference here? Or when I did my random selection, is this just normal variance within the randomness? Yes.
You know why it's 30?
I don't. And it's weird to me that it's like, you would think it would be like 5% of the population or something like that, right? But it's not dependent upon the population size. It may be that that's an empirical result where people said, let's try, 20, 25, 30, 35, 40, and they found out that once you get past 30, you don't get a change in results. It may be, or it may be that there's an actual derivation as to why it's 30. The F-test we don't talk about that much. Yeah. Oh, you remember the Z table? You're going to get a different table for Z and T. Yeah, but the formula, look, it's the same, right? But then you're going to get a different table. And I'm not going to run through that. I'll just run through the Z test since that's the one we normally use. The F test. And I can't remember the cutoff value, but basically the F test is basically comparing the fatness of the two samples, right? So sigma X and sigma Y are the observed standards of deviations for two samples, and then you are squaring both of them. Why do you square both of them? Because if you remember, the deviation was a square root term, so they're trying to pull that back to a value that makes sense within the population. And like I said, I can't remember what the cutoff value is for the F test. The chi-square test, which we often, again, we don't talk about that much. I like. Here's what the chi-square test is doing. I need to fix my notes again. That it's determining the likelihood that the two sets of outcomes aren't just matching each other in terms of average, but the actual shape of the curve is similar. So if I had two curves and one looked like that and one looked like that, you could see if you just did the averages and the z-test, it's effectively the same curve because the average is the same and the variance is the same. But these are clearly not the same curves. So what the chi-square test is doing, it's going down observation by observation, and it's comparing this node to this node, this node to this node, this node to this node, and you're getting these distances. And because it's squared, that's to get rid of the negatives, right? And so what's going to happen is you might have, according to these two curves, basically identical mean, identical variance. It looks like it's the exact same curve. And then when you do the chi-square test, you're going to find that you've got this massive value for chi-squared because none of the points actually lined up. Whereas if you had two curves that look like this, the means will be slightly different, let's say. But notice it's very, the shape of the curve is very similar because you've got this very small distance between all of the observed points. Does that make sense? So I kind of like this one because it's giving you more information than just the average. It's actually giving you information across the length of the series of measurements to determine if the shapes of the curves match up. Now, we have to be really careful. Notice what it says here. This is the ith observed measurement. That means you can only do this in situations where the sequence in which you do your measurements align repeatedly, right? Otherwise, you know, if it's truly random, like let's say we have 30 students in the class, and the first time I go through alphabetically, and then the second time I go through and pick students randomly off the roster, then the ith terms are not going to line up, right? So you have to be able to repeat the observations in such a way that there really is a correlation between the two sets of observed measurements. And then again, I've not I bring this up, but I'm not doing an example with it. If you want, we can do one tomorrow. But there's tables that tell you what the cutoff values are for these things, right? Where does it really look good? Or you can simply compare and have an arbitrary value for when you think that the curves are aligned sufficiently for your purposes. Okay, in statistics, I would hope they covered this test. Did they? I'm sure they did z-test. I'm sure they did t-test. What else do they do? Been a while.
But I've learned chi-squared in other statistics. For instance.
Yeah, chi-square, f-test, you tend to learn when you need to learn them, like they show up in an application usually. So what, 412 just does z-test?
It goes through all three. But for the chi-square, it gets like at the very, very end. It's not very.
They're out of semester at that point.
Yeah.
Okay. I pulled up some examples from the web on the z-test, and so the idea again is, let's go back here. Whoops. Let's go back and look at z-test formula, and again, what you are comparing is you are comparing two means. And then when you look at the z-test table, we've got this bell curve. Now, here's the thing you need to be aware of, though. What is that bell curve representing? Kind of nuts. It's remember, you're dealing now with two entities, the two averages. So this bell curve is representing the probability of these two averages aligning. It's like a meta curve. And right in the middle here, if the two averages aligned perfectly, what would be the value of the z-test? You would get average minus average, but they're the same value, right? So you're going to get 0. And then the value of Z would be 0. And if you look at the value of Z being 0, there's your 50, right? Oh, they're saying, okay, half the curve is to the left in this case. Which would make sense. Because these two have lined up right here, so the likelihood that one of them is off to the left is 50%. So, what are you looking for? You're looking for enough of this curve to be filled where you're saying the result that you got is only some small percentage. And then we're going to say, okay, if it's that level, then we're going to claim that there was a real effect. Otherwise, it was just dumb luck. And generally, it's 0.05 is what you pick. So generally, you want the portion of the curve not covered to be 0.05. You want this to be 0.95. So how does the z-table work? You look for, where am I at? 0.95, which is right in here. Oh, I can't mark it. Okay, so if we look, we want to be at, where did it go? 2, number 3, and 4, right in here. And so that's a z value of 1.6, 1, 2, 3, 4, 5, like 1.645. Halfway between these two. That's generally, and again, that value of 5% is kind of, somebody pulled it out of the air a long time ago and everybody said, oh, that's kind of sounds good, let's use that. And so that is a standard that you'll see quite a bit. But you can choose the level of confidence or the level of discrepancy that you want. So 0.5 is going to be that, which means if the z value is 1.645 or greater, then we're going to claim that this was, the effect was an actual effect and not just due to dumb luck. All right. Now notice what I'm talking about here, though, is filling the curve all the way from the left to the right. You'll hear the term one-tailed and two-tailed. This is one-tailed, where we're only considering this part of the curve. For a two-tailed, you have to figure half of it goes on each side. And so instead of doing 0.05, you do 0.025. That's the only difference. So if we look at these examples, by the way, this page is not a bad page, right? All right, so the teacher claims that the mean score of students in his class is greater than 82 with a standard deviation of 20. Sample of 81 students was selected and a mean score of 90. See if there's enough evidence to support the claim. Now, frame it as the question, are these two things the same? Basically, this is an arbitrary value. We don't know where these numbers came from, right? The teacher says that the mean score is 82 with a standard deviation of 20. That's a lot, because that puts students at 102, right? So it must be on the tail end, on the lower end. Anyway, 82 with a standard deviation of 20. And then they said, okay, I sampled my students and I got a mean score of 90. And the trick here is, are we claiming that those students are different, right? Better, in this case, than the general population? Or are they the same as the general population? You're always asking that question. Is it different or is it the same? So once you go through this route, then when you get these values, then the actual z-test is trivial. Okay? The average is 82, so the null hypothesis says the average is going to be 82, and then rejecting the null hypothesis is that the average is greater than 82. Now, what we mean by the average is 82, that's the null hypothesis. Well, why wouldn't you just say, well, shoot, the average was 90, we measured it, clearly the null hypothesis is not right. I'm done, right? How come I can't say that? It's an easy thing for people to say, by the way. I mean, clearly the average is not 82, it's 90. So null hypothesis, I don't even have to do the z-test. I can reject the null hypothesis. I'm asking you. I'm asking you why I'm wrong. Why am I wrong?
Because you could have just gotten lucky, right?
Exactly. Exactly. So, and that's what the z-test is telling you. Is this truly statistically likely to be different? You can't ever say it's different. You can only say it's statistically likely to be different. Or did you, right? Did you just get lucky and they really are the same? That's what we're asking ourselves. So you say, okay, the average is 82. And what we're saying here is, you know what, the average of all your students might be 82, but you just got lucky by picking the 90s, or you cheated or something. All right, so then we do get the equation. The equation is simple enough to plug in, right? We get x bar is 90. That's the one that was observed for the new students. The normal population is 82. Standard deviation is 20. So there's sigma. And our n, we did 81 students. That's a weird number, but I think they did it because square root is an integer, right? Doesn't matter. So then you get that. And then you say z is equal to 3.6. And we said, look, we needed it to be 1.645, z to be 1.645 was our cutoff point. If it's anything greater than 1.645, we're up in that little 5% area of the curve, which means this is 95% likely due to an actual change in the students, a difference in the population. It's only a 5% chance that it's dumb luck. And we're going to call that good enough.
So this is saying then that there's only a 5% chance that we sampled 81 students and they ended up having a mean of 90. Is that what this is saying?
Let me make sure I parse that
Well,
sentence
more
right.
than, I guess 3.6.
Yeah. Yeah, it's actually worse than that because because the z is
There's
2.6.
Like
There's like a 2% chance that this was dumb luck. Yeah, and we're saying if it's a 5% chance or less, then we're going to accept that it was really an actual change. The populations are truly different. Yeah. This is a one-tailed test. I'm going to go off topic in a minute. Now, this guy, I don't know this chart. I didn't read the rest of the lectures to get this chart. I just wanted these examples. So here's the one-tailed test. Population of all verbal GRE scores are known. Notice they're known to have a standard deviation of 8.5. And then the psychology department wants to receive applicants with a verbal GRE scores of over 210. And this year, the mean verbal scores for the 42 applicants was 212.79. Now, notice what they did here. They didn't say that the average GRE score was 210. They said that was a goal. So their goal population is 210 with the known mean of the known variation of 8.5. That's their goal. And now what they're asking is, that's my goal population. Is the population of students that I accepted, is that the same or better than or different than the goal? So they got 42 applicants, 212.79, and they're using this alpha 0.05. In other words, that's their cutoff, 5% chance that it's just dumb luck. Exact same process. Now they do it a slightly different way because they put this sigma x bar, but that's sigma over square root of n, so that's sigma over square root of n down here. They just put that in as an extra step. So it's the exact same process. You subtract the two means, you divide by the sigma over square root of n, and they ended up with 2.13, and we know that 1.645 is the magic number, so it looks like they're saying that they truly did exceed their goal. Their population of students that they accepted is better. a couple of little wrinkles in this. One is there are 42 applicants. In terms of the applicants, that was the complete population, right? That wasn't just a sample. That was the complete population. So that's kind of an interesting take. Yes.
Do they just know the standard deviation of population?
They know it's 8.5. And they just magically know it for this question. In reality, that's going to be published because if the GRE scores are the results of GRE scores are going to be published and discussed and blah blah blah. So they would know nationally or even internationally what a normal school, what the mean is and what the standard of deviation is.
So
Now they didn't care what the mean was of everybody taking the GRE because their goal was 210, so they're using 210 as their desired mean.
okay, but then that 8.5 that refers to everyone.
Yeah. So can we find any flaws in this argument? Yeah, because there's selection bias. If the students are going into the psychology department, maybe students who want to go into psychology are way worse at GRE or way better than GRE, or maybe their mean is not 8.5 because that's the general population. Maybe the mean for psychology people is 12. We don't know. So you can find ways to make arguments with the statistical reasoning. And generally you should. Sometimes people do it to be jerks. Sometimes people do it because they're being paid to do it. Sometimes it's legitimate. Are we really getting at the right answer? And then this is the graphical form of all that. By the way, this is the same line from the table that we saw earlier, right? I just segmented out the portion of the Z table that's interesting. And then there's a second one. This is the two-tailed test. And they say, suppose you start up a company, has developed a drug that's supposed to increase your IQ. Standard deviation of IQ in the general population is 15. You test your drug on 36 patients. That's not very many. And obtain a mean of 97.65. And again, we're going to use an alpha of 0.5. Is this IQ significantly different? Now, this is a two-tailed test, and I'm going to ask you, well, let's just do it. And then I'm going to ask you, why was it two-tailed to begin with? Same trick, right? They get the standard error of the mean, right? They just the exact same. All they do, once you have these values, it's just plug, look it up on the table. And basically, if you know that your alpha is 0.05, if you know that it's the 5% that you're shooting for, you know right off the bat, this thing has to be greater than or equal to 1.645. It's that easy. Once you get through the underlying assumptions, it's that easy. So they got minus 0.94. And then because they're looking at two-tailed, it's 0.05 divided by 2, right? They put half on each end of the scale. And then for 1.96, they're looking at kind of weird to read. Area between mean and Z, 475 and beyond is 0.025. And so we're looking at, where's the mean? Mean and Z. And so what did we end up with? Oh, they wanted a critical value of 1.96. And they got a critical value of what? Negative. Blah, 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 blah. So anyway, they ended up with this much of the curve being attributed to them, this much of the curve outside, which was not enough, right? They wanted only 2.5%, 2.5%, and instead they got all this. My main question here is, why the heck was this a two-tailed? Why was the other one a one-tailed and this was a two-tailed? When do you make that decision? And there's one word in each problem statement that will tell you. The word in the first problem statement is this significantly greater? That implies directionality, doesn't it? And for the second problem statement, is this significantly different? Significantly greater only goes in one direction. Significantly different could be greater than or less than. So that's how it's the framing of the question, right? Okay, so what does this mean for your projects? How does this get implemented? Almost certainly, if you're doing a true experiment, what you're doing is running some kind of a baseline scenario, modifying a variable, like we talked about experiment design, and then running the scenarios again with the modified variable. And then you have to figure out, did that variable change anything? And so you have metrics that you are hopefully just coming up with, and these were what your research questions with the hypotheses were. You're having metrics that you want to measure, and what you're going to find is because you have agent-based systems with variable results, you're going to run these experiment scenarios some number of times. You're going to get a mean and a deviation for the results for this metric. Then you're going to inject the change in the variable, run the scenario some number of times, get a mean and a variation for the new scenario, and then compare the two and see if the measurement from the mean was actually what we call statistically significant. And then when you frame it, you can't generally say, oh, improve, adding this variable improved the system by 10%, something like that. People commonly say things like that. But remember, you do have to frame it as it is statistically likely that these results were due to, right? That kind of thing, right? How many times should you run the scenarios? Well, if we want more than 30, population of 30, you might want to run your scenario 50 times. So when you're building these things, build them with a loop built in, right? Where it'll run the results and then it'll do some kind of saving of summary results, saving of something that you're interested in. If you are interested in 4 or 5 metrics, it may be that the only thing you need to save from each scenario execution are the results of those 5 metrics. If you are interested in really super detailed things, maybe you have to save a lot of state along the way. So like for a fuzzy cognitive map, should I save the value of every node at every iteration? I don't know, right? Depends on what you want to do. Or should I just save like maximum and minimum values for each node across the entire run, and then save how long did it take for this thing to propagate an effect throughout the system, things like that. Those are questions that are hard to answer. We talked to you yesterday about maybe saving everything and then having another piece of software analyzing. Maybe. If you don't save it, you still need some kind of history to be able to analyze, because it can be difficult to figure out when those things have actually converged. If they don't converge to steady state, then it's really tough to figure out if it's converged like to a periodic state or if it's just chaotic. Any questions about how you might use this in your experiment? Okay. I'm gonna turn this off. We can do talking. Tomorrow's project work day. Let me talk about that for a minute. How do I?